Alright, so back again with our next question. The graphs of y equals the square root of x minus a and y equals the square root of 2x minus x squared have the same gradient at their point of intersection. Find a, the point of intersection. Gradients, what does that mean? Gradients mean that I'm looking at derivatives, and the derivatives will be equal, and they will also intersect at that point, so at that point the functions will be equal. That's going to give me two equations, two unknowns. We should be able to find all the information that we need. Let's see if we can do that. Let's just start by finding the gradients. So if I have y equals the square root of x minus a, x plus a, remember that's the same as x plus a to the power of 1/2. So dy dx for that particular function is equal to 1/2 x plus a to the negative 1/2, multiplying by the derivative of the inside, which in this case is just 1, isn't it? Remember, a is a constant, it's not a function, so we don't need to worry about implicitly differentiating that. How can I write that nicely? Well, it's a 1 times 1 on top, and it's a 2 root x plus a in the denominator. What about my other function? Let's try and keep them clear here. I'll try a different color maybe. So here I have y equals the square root of 2x take x squared. I want to go ahead and write that with an index to make it a little bit easier for me. It's the power of 1/2. Therefore, dy dx, chain rule, derivative of the outside of the brackets, half 2x take x squared to the negative 1/2, multiplied by the derivative of the inside of the brackets, which is 2 minus 2x. Okay, can we make that look a little bit nicer? Yes. That's 2 minus 2x over 2 square root of 2x take x squared. So we know at the point of intersection, these two things are equal to each other. Okay, well, let's write that down. At the point of intersection, one over 2 root x plus a is equal to 2 minus 2x over 2 square root of 2x minus x squared. Some of you will already be saying, why haven't I cancelled that factor of 2? I think we might as well do it now just to make it look prettier. So 1 over 2 square root of x plus a equals, you can see that numerator factors to 2 outside of 1 minus x, doesn't it? So I'm going to cancel the common factor of 2. So now I've just got 1 minus x over the square root of 2x take x squared. Those two things are equal. But it's at the point of intersection. So what else do we know are equal? The original functions. What were the original functions? Square root of x plus a. And that will be equal to the square root of 2x minus x squared. Okay, so we've got two different equations, two unknowns. We should be able to get somewhere with that. And if you look at what they've given us, it looks nasty at the moment, doesn't it? It looks like, oh, we've got all these square roots, x's and a's. To get a on its own is going to be really hard. To get, the x on its own is going to be really hard. This is not going to be nice. But look at that information. If the square root of x plus a is equal to the square root of 2x minus x squared, I can make that substitution into the first expression over here. I'm still going to be getting rid of the a, so I'll still have an equation with just one unknown. That's going to work, but I don't need to overcomplicate it by trying to get a weird expression for a, which is going to be overly complicated. Let's just make that substitution right now as it is. So I'm going to say, let the square root of x plus a equal the square root of 2x minus x squared. So now I've got 1 over 2 times the square root of 2x take x squared equaling 1 minus x over the square root of 2x take x squared. Wow, that looks a lot nicer already, doesn't it? What am I going to do? Well, I'm going to get rid of this next nasty bit. Each side is being divided by the square root of 2x minus x squared. So if I multiply each side by the square root of 2x take x squared. Those terms are disappearing from my denominator, aren't they? As the terms disappear, what am I left with? Oops, my pen's disappeared as well. That was tricky. I've now got 1/2 equals 1 minus x. Wow, that's looking a lot nicer. Subtracting 1 from each side, I have negative 1/2 equals negative x. So x is equal to 1/2. All right, I'm on my way. I've found one part of the equation. What am I going to do? Let's substitute that x equals 1/2 into this second equation and go on from there. So I'm going to say let x equal 1/2 in equation 2. That is going to let me solve for a. So what have I got now? I've got the square root of 1/2 plus a, and that's equal to the square root of 2 multiplied by 1/2 minus 1/2 squared. Well, if the square root of something equals the square root of something else, then what we're square rooting must be equal, so I can just get rid of those. So I have 1/2 plus a equals 2 times 1/2 is 1 minus 1/4. What's a equal to? It's 1 minus 1/4 minus 1/2, subtracting 1/2 from each side. A is equal to 1/4. All right, so x equals 1/2, a equals 1/4. Have I found everything? No, I wanted the actual point of intersection. So the last step is to find the value of y. So I'm going to sub x equals 1/2 and a equals 1/4 into y equals the square root of x plus a, which was the first equation we were given. Therefore, y is going to equal to the square root of 1/2 plus 1/4. Y equals the square root of 3/4, and you get excited here because that's going to be root 3 over 2, and you can remind yourself of all that exciting trigonometry that you used to do with exact value trig functions. Wow! A little bit complicated. The key step, I've gone back and highlighted it here for you. Let's have a look. I'll even put the highlighter over it. That was the key step, wasn't it? In trying to do the simultaneous equations, whilst you could use your calculator, you're going to run into all sorts of problems. This is a nice way to do it. Square root of x plus a. Let's make that substitution to get rid of the a, rather than trying to rearrange this and getting a really difficult thing to substitute in. I hope that helps. I will see you in the next video. Keep the questions coming. It's really good. Cheers, guys.